Good morning. Assalamualaikum, everyone. Welcome to my lecture 16 of CHM 577. Today we are going to talk about coordination compounds. Thank you to Dr. Amalina for the notes which I'm presenting for my students. And I have supplemented the notes with my own additional notes there. So let's begin. What are coordination compounds? Now, coordination compounds are sometimes called complexes. They contain complex ion and counter ion. And what is a complex ion? A complex ion is when you have central atom, which is the metal, the central metal, usually, of course, the transition metals. It's really very unusual if you have coordination compounds that contain metals that are not transition metals. They will have to be transition metals. So these transition metals surrounded by ligands, when that entity is carrying a charge with it, we call it a complex ion. And that charge of the complex ion is being countered or by being neutralized by the charge of the counter ion. So for example, okay, before I give you an example, a complex ion contains a central metal atom or cation. It can be a neutral metal, or it can also be a charged metal, which is a cation of transition metals surrounded by ligands. So looking at this picture here, can you see this picture that I am touching with my cursor? You have cobalt right there in the middle. You have 6 ammonia, one at the top, one at the bottom, one on the right, one on the left, one at the front, and one at the back. So you have 1 cobalt surrounded by 6 ammonia. Of course, we know ammonia does not carry with it any charge. So ammonia is a neutral molecule. So the neutral molecule is bonded to cobalt, 6 of them. So cobalt here is a cobalt 3. How do I know it is a cobalt 3? Because the whole thing has to be neutralized, the charge of the whole thing in this bracket. So this bracket represents the complex ion. The charge of the complex ion has to be neutralized by 3 chloride ions. That means it's telling me that this bracket carries with it a 3 plus charge, and the 3 plus charge comes from the cobalt itself because the ammonia does not carry any charge. So the central atom is cobalt 3 plus. The ligands are 6 ammonia molecules, and the combination of this central atom with the ammonia molecule we call complex ion, and the chlorides we call them the counter ions. The second example is the one on the right here, where you have platinum surrounded by 4 ammonia molecules that act as a ligand. I'm going to tell you what is a ligand in a while in the next slide. So you have platinum, 4 ammonia, and 2 bromide outside acting as the counter ion. So again, the 2 bromide carry with them 2 minus charge. So we know that this entity that is in this square bracket, or the complex ion, has a charge of +2 because it needs 2 bromide to be neutralized. So the +2 charge will not have come from the ammonia, it will come from the platinum. So your central atom is platinum 2 plus. Your ligands are 4 ammonia molecules, and this combination of the platinum 2 plus and the 4 ammonia molecule make your complex ion in this case, and the charge of the complex ion is neutralized by the bromide. So that is a coordination compound. Yeah, that is one type. Of course, there are other type which we will go through as we go along in the next coming few lectures. So I mentioned to you the word ligands. This is probably the first time you're hearing the word ligands. What are ligands? Remember, they're not ligands. Ligands is wrong. the pronunciation is ligands. Now, ligands are molecules or ions having one or more donor atoms that could donate lone pair of electrons. Lone pair of electrons. You all know what are lone pairs of electrons? They are the pair of electrons that is not being used in bonding, just the dots, yeah, the dots. And the ligands are acting as electron donors. And if you recall the Lewis definition of acids and bases, all electron donors, we call them Lewis bases. So your ligands are Lewis bases. And where do these lone pair of electrons go? Who are they donated to? They are donated to the metal centers. So the ligands donate the lone pair of electrons to the metal center. The ligands are the electron donors. The ligands are Lewis bases. Metal centers are electron acceptors, and by such, they are called the Lewis acids. So when metals accept the donated lone pair of electrons from the ligands, what is formed is called a dative covalent bond. Why is it a covalent bond? Because the electrons are being shared between the ligand and the metal center. When the electrons are being shared, you form a covalent bond. But what kind of covalent bond? Dative covalent bond. What is the difference between covalent bond and dative covalent bond? I'm going to go through that with you in a while. Before, I would like to show you the mechanism. Now, this is not originally in Dr. Amalina's notes. I'm adding it for further clarification on the um, bonding of ligand to metal center. So take this metal center, for example, M, which has a hybrid orbital that looks like this. Yeah, a hybrid orbital that looks like this, empty hybrid orbital on the metal. And here is your ammonia. Can you recognize that this blue and 3 whites are actually nitrogen and 3 hydrogens? This is ammonia, yeah, ammonia ligand. And the lone pair of electrons of ammonia is sitting on that lobe. Remember your VSEPR? This is in fact your ammonia. So this lone pair of electrons that are sitting in the lobe at the top is donated by the nitrogen to the metal to form a dative covalent bond. So this, can you see the 2 red dots there? Let me highlight. I don't know whether you can see it. The 2 red dots there, the 2 electrons that make a lone pair being donated to the metal atom into this empty hybrid orbital. So your ligand is acting as a Lewis base electron donor, and your metal is acting as a Lewis acid and electron acceptor. Donation of lone pair of electrons from your ligand to your metal. What is formed is a coordination compound where the metal and the nitrogen share this electron pair. And the electron pair comes from the nitrogen, the lone pair of the nitrogen. So the resulting bond is a dative covalent bond. So I'm going to quickly run through with you the difference between a typical or an ordinary covalent bond and a dative covalent bond, which is also called coordinate bond. Now, in covalent bond is formed when each bonded atom contributes 1 electron to be shared, forming the bond. For example, you have your hydrogen here, you have your chlorine here, excuse me, you have your chlorine there. When hydrogen and chlorine each donate 1 electron, and that pair of electrons are being shared between the hydrogen and chlorine, you have HCl, and the bond between HCl is a covalent bond. Yeah, so that is a typical covalent bond where the shared electrons, one comes from hydrogen and another one comes from chlorine. But dative covalent bond is when both the shared electrons come from only one of the bonded atom. So this is it. This is the example. These shared electrons only come from this nitrogen, none from the metal. So this covalent bond is called a dative covalent bond or a coordinate bond. Now, most donor atoms come from group 5, either nitrogen or phosphorus, group 6, oxygen or sulfur, and group 7, halogens. And there are 3 classes of ligands. You have monodentate ligands, bidentate ligands, and polydentate ligands. So what are dentate? Dentate comes from the Greek word dentis, yeah, teeth, gigi, yeah, gigi. So when the ligand bites or menggigit the metal on one location, it is called a monodentate ligand, the ligand that can only bite at from one donor atom. But if that ligand contains 2 donor atoms, then you call that a bidentate ligand, where the 2 donor atoms can both donate one pair of electrons each to the metal. So this donor atom donates one pair, this donor atom donates another pair. So you have the metal bonded to that bidentate ligand on 2 points. So the gigitan, the bite, is on 2 points for bidentate ligand. And on the same note, when you have polydentate ligand, is you have more than 2 donor atoms, and you will see a few in this lecture later. So that's about ligands. So I'm still talking about coordination compound. Remember here, coordination compound, I was talking about the the complex ion and so on and so forth. So in order to maintain charge neutrality in the coordination compound, because when you have a coordination compound, the word compound implies that it is a neutral moiety. It does not carry with it any charge. So whatever charge that is carried by your complex ion is being neutralized or being countered by a counter ion. So to maintain neutrality of charge in the coordination compound, the complex ion is typically associated with counter ion, yeah, like you saw in the previous example in slide number 1. And the complex ion is always written enclosed in a square bracket. Look at this here, yeah, you have the square bracket. A coordination compound behaves like an electrolyte in water. So when you put, not necessarily in water, maybe in different solvents, whatever solvent it is soluble in. So when you put your coordination compound in any solvent and when it dissolves, the complex ion and the counter ion will separate from each other. The complex ion will be an entity with maybe a positive charge. So if it is a positive charge, then your counter ion must be negatively charged, or vice versa. If your complex ion is negatively charged, then your counter ion will have to be positively charged. So the example that's given here is cobalt with 6 ammonia, and ammonia only has one donor atom, nitrogen. So it's a monodentate ligand. So cobalt with 6 ammonia in square brackets. So it is clear to us from here that this is the thing that's written in the square bracket is complex ion, and Cl3 is the counter ion. In solid condition, they do not separate. They do not, just like any other salt, they do not contain ions. But when you dissolve it in solvent, for example, water, it will separate. The 2 ions will separate. The complex ion will separate as CONH3 plus, and your 3 chloride will separate as 3Cl minus counter ion. So this is the picture. You have this picture as a solid where the counter ions and the complex ions are not separated, but in solution they are separated as shown in the drawing here. However, The complex ion here, this one here, the complex ion behaves like a polyatomic ion, an ion that contains many, many atoms. The ligands and the central metal ion remain attached in the complex ion. They do not get separated upon dissolving in any solvent. Yeah. Now, from the textbook Martin Silverberg, this is taken, which is some common ligands in coordination compound. In Silverberg, it is mentioned as unidentate. Some textbook call it monodentate. It's all right. Both carry the same meaning, one tooth or one donor atom. Examples of monodentate ligand is water. In water, you have oxygen as the donor atom. Why oxygen you know as a donor atom? Because the oxygen carries with it the lone pair of electrons. If you can still recall, ligands are neutral molecules or ions that has donor atom containing lone pairs of electrons. So anything that has lone pair of electron is your donor atom, and you use the number of donor atom to determine the type of the ligand, being monodentate, bidentate, or polydentate. So other examples of monodentate ligand is ammonia, of course, with nitrogen as the donor atom. Fluoride ion, of course, fluoride. Chloride, of course, chloride, nothing else. But cyanide, C double bond N, you can either, the choice is between carbon as a donor atom or nitrogen as a donor atom. So how do you decide? How do you decide which one for the cyanide ion? Both have lone pair of electrons. So which one will be the donor atom? So the choice is by looking at the electronegativity value. If the electronegativity value is high, it is going to hold on to any electrons very strongly. It's not going to be able to give the electron very easily. But any donor atom will have to be able to give away its electron, and between carbon and nitrogen, nitrogen is more electronegative than carbon. So your carbon is your donor atom in this case. The second example here, next one is OH. OH is pretty clear that oxygen is the donor atom because hydrogen doesn't carry with it any lone pair of electrons. But what if you have a choice? If you have sulfur and nitrogen, if you look at the value, electronegativity values, there are certain times that sulfur will be the donor, certain times that nitrogen will be the donor. And depending on who is being the donor atom, the behavior or the name even of that ligand will change. Yeah. The same with here, NO2. NO2 can donate electrons from oxygen or from nitrogen. When it donates from oxygen, then you have a different name for it. When it donates from nitrogen, it has a different name. We will go through this when we go into isomerism later. Okay, so that's the story about unidentate or monodentate ligands. These are some typical common monodentate ligands that have been listed at the top. Now, the second type of ligand is called the bidentate ligand. Bidentate ligand, as you can recall from the previous slide, that it contains two donor atoms that can donate lone pair of electrons. So look at this ethylene diamine, NH2, CH2, CH2, NH2. You can very well see that the two nitrogens, this one here and that one there, both of them, they contain lone pair of electrons, and both of them may or can donate those lone pair of electrons to the metal to make dative covalent bonds. So both of them will connect to the metal, and this ligand is called a bidentate ligand because it binds at two positions. Yeah. Same with your oxalate. Yeah, oxalate is CO2, CO2. Yeah, this is oxalate. So you have two oxygen donor atoms. So oxalate is another example of a bidentate ligand. Now have a look at polydentate ligand. Polydentate ligand is when you have more than two donor atoms. One example is diethylene triamine. So diethylene, ethylene is CH2CH2. There are two of them, so it's diethylene. But the amine, there are three of them. One, two, and three. So you have diethylene triamine. So that is a tridentate ligand, or being a general name of polydentate. The next one is triphosphate ion of this nature, and the most famous one is EDTA, ethylene diamine. Can you identify the ethylene diamine part? This is right in the middle. Tetraacetate, four acetate. So one acetate at the top, one acetate at the bottom on the left, one acetate at the top right, and one acetate on the bottom right. So there are tetraacetate, and in the middle it is ethylene diamine. So it is simply called ethylene diamine tetraacetate, or EDTA. So EDTA is an example of a ligand, a polydentate ligand that has six donor atoms. So NOO on the left and NOO on the right. In the next slide, you are going to see how these six donor atoms can encapsulate a metal center. Yep, this is another representation of your monodentate ligand, your water, very clear. On your oxygen, you have two pairs of lone electrons. Ammonia, on your nitrogen, you have one pair of lone electrons. Chloride, cyanide, carbon monoxide even. Carbon is the donor atom because carbon is less electronegative or more electropositive than oxygen. And CS is a thiocyanate ion hydroxide. And then next one is your typical bidentate ligand, your ethylene diamine, your glycinate ion. This is a glycinate ion, yeah. And lastly, your oxalate. And I'm going to skim right through into your polydentate. EDTA, you have known what is EDTA, ethylene diamine, which is this moiety right in the middle that is making the skeleton. Tetraacetate, one acetate, two acetate, three acetate, and four acetate. So ethylene diamine tetraacetate, EDTA. And how does this EDTA encapsulate a metal center? For example, a lead here. So the two nitrogens, 1 and 2, are these two nitrogens, 1 and 2. It binds on the right-hand side of the lead. One acetate from the top, the second acetate from the bottom, the third acetate from the left behind, and the fourth acetate from the front on the left. So 1, 2, 3, and 4, 5, and 6. 6 donor atom is totally surrounding that lead. And this is very, very important in the in our life because EDTA can be used as a heavy metal scavenger. Scavenger means something that can remove, encapsulate that very, very dangerous heavy metal in our body. If you have heavy metal poisoning, chances are doctors will get you to drink EDTA, and EDTA will come into your body and it will bind onto that poison of heavy metal, removing it as your stool. When you go to the toilet, it gets removed. The heavy metal gets removed and gets deactivated when it is encapsulated by EDTA. Another use of EDTA is as a preservative or additive in your shampoo, because putting EDTA in shampoo or in soap will remove any free radicals, any metal, trace of metal cations that will promote your soap getting bad or getting rancid or getting oxidized. So when the metal cations or whatever impurity is being encapsulated by EDTA additive in your shampoo will last longer. Yeah, to increase the shelf life of the shampoo. So EDTA is really quite a useful little ligand, polydentate ligand. Now, when we talk about bidentate and polydentate ligand, usually those bidentate and polydentate ligand cause rings in the complex ion. What do I mean by rings? Look at this. There is one ring here. Can you see? There's another ring there. There's another ring and many rings. Yeah, when you have polydentate. What is the significance of ring? Ring means stability. Ring will increase the stability of that particular um, substance. Now, the ligand appears to grasp the metal between two or more donor atoms. Therefore, these ligands are also known as chelating ligand. Chele, C-H-E-L-E, is from Greek word translating to English as claw ataupun claw macam ketam punya sepit, ketam punya sepit, the claw, so it is kill. So any ligand that can bite at more than 1 point, either 2 points, you call it as a chelating ligand. Chelating or menyepit, menyepit, claw. The complex ion that contains these dentate ligands, polydentate, are called a chelate. Yeah, chelate. Chelate ligands makes complexes more stable. So when a ligand has chelated onto the metal, what is produced is a very stable compound and it's not going to harm anybody because it is encapsulated, it is made inactive, and you can remove it. And when you compare the stability of a chelate ligand and a monodentate ligand, you will definitely see, we will go through this later in next lectures, a few more lectures from now, that chelate compounds are more stable than monodentate compounds. Yeah. So bidentate is like this. So if you take ethylene diamine here, NH2, CH2, CH2, NH2, you take 3 of them, one at the top on the right, one at the bottom on the right, on the left, I'm sorry, on the left, and then another one on the right. Oh, this is right, correct, yeah. I'm confusing left and right. So in that way, so you have 3 bidentate ligands coordinating to a metal center right there in the middle, and this drawing can be simplified to look like that, to look like this on the right. Yeah, so 1 ethylene diamine, 2 ethylene diamine, 3 ethylene diamine can be represented by this and this and that. But that is just a simplification. The same thing can happen for oxalate as well, because oxalate also is a bidentate ligand. Now, what is the nature of metal to ligand bond? I have explained to you that when a ligand bonds to a metal, the ligand donates its lone pair of electrons to the metal. The metal will accept it. So your metal is your Lewis acid and your ligand is your Lewis base. The bond between a ligand and a metal is an example of interaction between Lewis acid and Lewis base. Metal cations, which are the transition metals, have empty d orbitals. I'm going to talk about this later. You just have to take it from me now that transition metals have empty d orbitals, so they can act as a Lewis acid or electron pair acceptor. So metal cations are electron acceptor, they are Lewis acid. And the ligands are the electron donor, so they are the Lewis bases. Yeah. So the relationship between your ligand and your metal is a Lewis acid base relationship. So we can picture the bond between metal ion and ligand as a result of them sharing a pair of electrons that was initially sitting on the ligand. Yeah. So You have your ammonia, two ammonia here. Yeah, two ammonia reacting with one silver cation, and the silver cation accepts the lone pair of electrons from each ammonia, one on the right, one on the left, and it makes a complex ion like that. Yeah, because your silver has a plus charge, your ammonia has nothing, no charge, so the plus charge is carried over throughout the complex ion within the square bracket. So when we talk about coordination compounds, there are two numbers that you have to be very mindful about. One is oxidation number of the metal. Oxidation number of the metal is the charge of the metal. Number two is the coordination number of the metal. The coordination number of the metal is defined as how many atoms, how many donor atoms have bonded to that metal. If there are two donor atoms bonded to the metal, you say that the coordination number of that metal is 2. If there are 3, you say coordination number of 3. If there are 4, similarly, coordination number of 4. If 6, coordination number of 6. So if you have, for example, I'm taking CuH2O here, 4 water with copper in a complex ion with a charge of +2. The cation is Cu2 plus. Kenapa? Because water doesn't carry with it any charge. So that 2 plus charge will solely come from the copper. It cannot have come from the water. So the cation is copper 2 plus. The ligands are 4 water molecules. The coordination number of the number of bonds around the metal center is 4. But this is a very interesting example that we have at the bottom here. Iron with 6 cyanide with an overall charge of 3 minus. Now, can you guess what is the charge of ion? Not ion, iron. Iron, the Fe. Now, everybody knows that cyanide is a -1 charge. Yeah. So 6 of them is -6. So if Cn is -6, Fe you do not know what, so you say it's X. And the whole thing carries with it 3 minus, so X minus 6 is equal to 3 minus, so X is equal to 3 plus. So your ion here has an oxidation number of 3 plus. But it has a coordination number of 6 because there are 6 cyanide that is bonded to your iron. So this is hexacyanoferrate. And I'm going to teach you how to name this in a while. Yeah. So I hope you now can distinguish how you work out, how you calculate the oxidation number of the metal and the coordination number of the metal. Oxidation number of the metal is the charge of the metal center, and the coordination number is how many bonds have been created between the metal center and the donor atoms surrounding it. Yeah, it's really quite simple. And the coordination number of that metal will determine the geometry or the shape. Just like when you learn VSEPR, when you have coordination number of 2, the 2 ligands around the metal will push each other away as far apart as possible, and you are going to get a linear geometry. Yeah, one here, one there, so you get a linear geometry. But when you have coordination number of 4, there are 2 possible shapes that you may get, or 2 possible geometries that you may get for 4. You can have square planar, you can also have tetrahedral. When do you get square planar? When do you get tetrahedral? That will be more clear when we discuss crystal field splitting. Never mind about that. Just take it for now. For coordination number of 4, it is possible for you to get square planar. It is also possible for you to get tetrahedral. The shape of square planar is this, and at the bottom there is the shape of a tetrahedral complex ion. And these all on the right hand side are examples of such complex ions. And if you have coordination number of 6, the shape or the geometry of that complex ion is octahedral. Octahedral looks like this. It looks like a pyramid. You've seen octahedral before when we learn VSEPR. Yeah. Now, this is a totally new addition to what Dr. Amalina has prepared. This is this slide. I want to show you when cobalt, this is one cobalt, for example, when it bonds with 6 ammonia, 1 ammonia, 2, 3 ammonia, 4, 5 ammonia, and 6. This is the lone pair of electrons on the nitrogen being donated to the cobalt into this hybrid orbital. Remember what is the hybrid orbital of octahedral? D2sp3, remember, or sp3d2. It can either be d2sp3 or sp3d2. So this is the hybridization, the sp3d2 hybridization of this cobalt octahedral. So each one of this hybrid orbital will accept one lone pair of electrons from the nitrogen of this ammonia. So one goes there, the second goes there to be shared, the third goes there to be shared with the cobalt. So what you effectively get is a cobalt with 4 dative covalent bonds. Now remember, there are 2 things that you must realize or you must remember when you are drawing the coordination compound. 1, a dative bond is always represented by an arrow, not a line. It's not simply a single line like covalent. A dative bond or dative covalent bond is always an arrow. It is an arrow that originates from the ligand to the metal. Why from the ligand to the metal? Because it is the ligand who gives the electron to the metal. So the ligand is the origin of your arrow going into the metal, following the direction of the electron donation. So remember, you have to draw an arrow for a dative covalent bond. And number 2, be careful to start your arrow from the exact donor atom. For example, ammonia. For ammonia, the donor atom is nitrogen, not hydrogen. So this is correct. I'm drawing this very, very carefully to show that this arrow comes from nitrogen into cobalt. Nitrogen into cobalt, nitrogen, cobalt, nitrogen, cobalt, and nitrogen, cobalt. But sometimes students, and sometimes lecturers too, they are so used to writing ammonia as NH3. And they draw it like this. So when they draw NH3 like this, the arrow comes from the hydrogen, which is wrong. So this is wrong. You have to consciously write your ammonia as H3N, like this. So that N is connected to the cobalt. So if you draw it like this, NH3 like that, where the arrow comes from hydrogen, I'm going to mark you wrong. But you must be careful to draw your ammonia or to write your ammonia as H3N rather than NH3 if the circumstances require you to do that. So this is right, this is wrong. Yeah. So that is just a reminder for you to draw your ligands and your arrows carefully. Now, what about the charge of complex ion? The charge of complex ion, do you still remember the charge of the complex ion? Here, yeah? Charge of this complex ion, no, not there. Sorry, huh? Charge of this complex ion, I've explained it to you, but I can explain it again to you. Yeah. The charge of the complex ion is actually the sum of the charge of the central metal with the charge of the ligand. For example, if you have copper 4 ammonia and sulfate as a counter ion, your counter ion sulfate has a charge of 2 minus. So what does that tell you about your complex ion? What is the charge of your complex ion? If your counter ion is 2 minus, then your complex ion must be 2 plus, because the purpose of a counter ion is to neutralize all the charge of your complex ion. So since the counter ion has a 2 minus charge, then your complex ion has a 2 plus charge, and you can determine what is the oxidation state of your copper by looking at that ligand. Ammonia again has a 0 charge. So the oxidation number of your copper there is 2 plus. Yeah, we can use the charge of the complex ion to calculate the oxidation number or oxidation state of copper. Because the ammonia ligands are neutral molecules, the oxidation state of copper must be 2 plus, because it's plus 2 of your copper added with 4 of 0 from ammonia is equal to plus 2. So if you don't know what this is, you put that as x, so x is equal to plus 2. Yeah. So you can use that information that I've given you for the past 41 minutes to try these questions, A, B, and C. So please try this question to calculate what is the oxidation number of rhodium here. Remember, ammonia has 0 charge, chloride has -1 charge, nitrate has -1 charge. Use this information to calculate the charge of RH, or rhodium. So question B, what is the charge of the complex that is formed by platinum 2 when it is surrounded by 2 ammonia molecules and 2 bromide ions? So you have your platinum in the middle, you have 2 ammonia attached to it, you have 2 bromide attached to it, so there are 4 ligands around it. 2 has charge, 2 are neutral. So what is the charge of the complex? So you work that out. Number 3, what is the charge of the complex ion that contains chromium 3, which is bound to 4 water molecules and 2 chloride ions? What is the formula of that moiety? So please work that out. I have the answer right here. I'm not going to show you yet. So we are going to discuss the answer when we have our live discussion. Right? Please remember to ask me. Now, lastly, I'm going to quickly cover about naming of coordination compound. There are a few rules when you name coordination compound. First rule is, in naming complexes, the name of the cation is given before the name of the anion, just like any other compound. For example, sodium chloride, you name your cation first, then you name your anion. So this same thing happens here. You always name your cation, whether it is a complex ion or it is not a complex ion. You name the cation first. Thus, if you have cobalt NH3, 5Cl, and Cl2, we name this complex ion first before the chloride. And how do we name the complex ion? Within a complex ion, the ligands are named before the metal. So you mention the name of the ligand. So when you have more than one type of ligand, the ligands are listed in alphabetical order. So chloride will have to come after amine, because amine is A, chloride is C. So alphabetically, regardless of the charge of the ligand. Prefixes that give the number of ligands are not considered part of the name in determining alphabetical order. For example, diaqua is not D, it is A. Aqua is water. Yeah. So diaqua will come first before trichloro, for example, because it is C, not the tri. Yeah. Thus, in CONH3 5Cl2 plus ion, we name the ammonia ligand first, then the chloride, then the metal cation. We are going to go through some example of this a little bit later. Number 3, rule number 3, the Greek prefixes of di, tri, tetra, penta, hexa are used to indicate the number of ligands when more than one is present. For example, if you have two chloro, you say dichloro. When you have three chloro, you say trichloro. If you have four bromo, you say tetrabromo. But if the ligand itself contains a prefix of this kind, for example, ethylene diamine, it has di already in there, you cannot say diethylene diamine. You have to use an alternate prefix, which is bis for 2, tris for 3, tetrakis for 4, pentakis for 5, and hexakis for 6. So if there are two ethylene diamine, you say bis ethylene diamine. Yeah. Next, the names of anion ligand, for example, Cl minus, Br minus, will always end with O. So you don't say chloride, you say chloro. You don't say bromide, you say bromo. You don't say iodide, but you say iodo. Cyanide, you say cyano. It always ends with O. The ending of names of the neutral ligands do not change. For example, amine for ammonia. You say amine, you don't say amino. No, you don't, because it is a neutral ligand. Neutral ligand, you name it as it is given, yeah? Special names are given to water, which is aqua. Ammonia is called amine. CO is called carbonyl. So if there are two water, you say diaqua. If there are three amines, you say diamine. If there are four carbon monoxide, you say tetracarbonyl. Okay? And if the complex ion is a cation, the central metal cation is named the same as the name of the element. For example, cobalt. Yeah? If cobalt is in the complex ion that is positively charged, the, the metal is called by its usual name, cobalt, the metal name. But if the complex ion is an anion or it carries with it a negative charge, the name of the central metal is ended with the suffix ate. For example, cobalt becomes cobaltate. When does it become cobaltate? It is when the cobalt is located in a complex ion that carries a negative charge. So if it carries a positive charge, you say ion 2, for example. But if it is an anionic complex, it is ferrate 2. Copper 2 becomes cuprate 2. Lead becomes plumbate 2. Lead is plumbum, but we say lead. Silver becomes argentate. Gold becomes aurate. Tin becomes stannate. Cobalt becomes cobaltate. Nickel becomes nickelate. Yeah. When the complex ion has a negative charge, you end the name of the metal with ATE. Yep. But the next one is, okay. The oxidation number of the metal is given in brackets in Roman numerals following the name of the metal. And remember, there is no space between the name of your metal with that alpha, with that numeral. So let me, yeah, no space. Ferrate, no space 2. Yeah. Cuprate, no space 2. If you put space, then you are wrong and marks will be deducted. So these are the names of a few common ligands. Br minus is bromo, F minus is fluoro, O minus is oxo, OH minus is hydroxo, Cn minus is cyano, C2O4 minus is oxalato, CO3 minus is carbonato, and CH3COO minus is acetato. Acetato. So all of this end with O. Why? Because the ligand has a negative charge. Yeah. bromofluorooxohydroxocyanooxalato carbonato acetato. But if you have a neutral ligand that doesn't carry with it any charge, ammonia is called amine, water is called aqua, NO is called nitrosyl, CO is called carbonyl, oxygen is called dioxygen, N2 is called dinitrogen. This pyridine is called pyridine, ethylene diamine is called ethylene diamine. So those are name of a few common ligands. So with that, I'm going to give you these 6 um, coordination compounds to name. Please name them. The answer is here. We're going to discuss the answers later. So please name number 1, number 2, number 3, 4, 5, and 6. And I'm going to ask you in the lecture later in next week. And the second question for naming is, please give the molecular formula of the following coordination compound. The formula: hexaamine iron 3 nitrate, ammonium tetrachlorocuprate, sodium monochloro. I would not say mono because mono usually you don't need it. Sodium chloropentascyanoferrate 2, potassium hexafluorocobaltate 3. And then this is changing from name to formula. Down here, please change this formula to names of the compound. This 5, 6, 7, and 8. Yeah? Practice exercise. These are your answers. I'm not going to reveal the answers yet. And you can also practice writing chemical formula: tetra aqua platinum 2, hexachloroplatinate 4, ammonium diaqua tetrabromovanadate 3, tris ethylene diamine cobalt 3, trioxalatoferrate 3. So give the chemical formula of all these compounds that are given in this page. And this is from your previous past year's paper. You consider the following compound: X is ammonium diaqua bisoxalato nickelate 2, and Y is tris ethylene diamine cobalt 3 sulfate. For each of the compound, write the molecular formula. You get 2 marks. What is the coordination number of central metal ion? You must draw it. You must draw the compound before you are able to determine the coordination number. If it is a bidentate, write 2. If it is a monodentate, write 1. State the electron configuration of the central metal ion. You must first determine the oxidation state of that metal. Then from that oxidation state, you can give me the electron configuration, the 1s2, 2s2, 2p6, blah, 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 blah. So I want that, right? So those are the questions that you have to try. It has been a 53-minute lecture for this one. I hope you understand everything. I hope you try all these practice exercises. And please ask me in class if you have any questions or anything that you do not understand. With that, thank you very much for listening. All the best to you. Take care, keep safe, and keep the motivation up. Bye-bye. Assalamu alaikum.